Hello everyone and welcome to Control Engineering Tutorials. In these tutorials we present real and applicable knowledge of control systems. So let's start. In this particular tutorial I will explain one very important method for tuning the parameters of the PID controllers. The name of this method is the Ziegler Nichols method, and the importance of this method lies in the fact that you don't need to have a model of the system in order to apply this method. That is, this method is purely experimental. So forget about Laplace transform, forget about all the complex math that's often involved in the design of control systems. Forget about it. You just go to your plant or to your system, you observe the output, you adjust the proportional gain until you see stable oscillations. Once you see the stable oscillations, you measure the period of the oscillation and you measure the proportional gain that produces these stable oscillations, and on the basis of these two parameters and a few formulas, you can immediately design the parameters of the PID controller. Here's the main question. Are the control parameters computed by using the Ziegler Nichols method optimal in the general case? And the answer is no, they are not optimal. Then the question is, if they're not optimal, why do we use this method for finding the control parameters? Well, we use this method because we want to find initial values of PID control parameters. Once we find the set of initial parameters by using the Ziegler Nichols method, we can simply tweak these parameters a little bit in order to improve our step response. So let us illustrate this process. This line over here shows the step response of the closed loop system when the control parameters are computed by using the Ziegler Nichols method. We can immediately see a problem over here. This closed loop system produces a large overshoot, and this is not acceptable. We want to basically reduce the overshoot. So how do we reduce the overshoot? We simply take the parameters computed by Ziegler Nichols method and we increase the derivative gain in order to increase the damping of the system, and we also increase the integral gain to have a little bit better rise time of the system. And as the result, we obtain this graph over here. Apart from explaining the basics of the Ziegler-Nichols tuning method, I will also present you another method for tuning the PID control parameters. This method combines the model of the plant and the Ziegler-Nichols tuning method. And the method that I will present is kind of a secret method. You can rarely find this method in books or in other YouTube video tutorials. Okay, but before I start, I would like to mention a few important things. First of all, those of you who are my subscribers or who watch my channel know by now that I always create a post that nicely summarizes everything that I will explain in this video. And here's the post. This post contains graphs, contains equations, and even it contains MATLAB code that you can find at the end of this post. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this video and this tutorial. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. First, we summarize the Ziegler-Nichols PID control tuning method. The goal is to experimentally determine the parameters of the PID controller. And here's our PID controller. Kp is the proportional gain. Ti is the parameter of the integral action. 1 over s is the integral action, and Td is the parameter of the proportional action. Here is the parameter Td. S is the derivative action. The first step in applying the Ziegler Nichols method is to eliminate the integral and derivative action. So we eliminate the integral action and the derivative action. This is done by setting TD to 0 and by setting TI to a large value, and consequently we are only left with the proportional controller. Let the plant or the system that we want to control be denoted by P. It's given over here. Then we have this block diagram. In this block diagram, Kp is our proportional controller, Y is the output of the system, and R is the reference or the desired signal. Assuming that the applied reference input is an impulse, in practice this can also be a short pulse, our goal is to find Kp that produces stable and persistent oscillations of the output signal. To repeat, over here we either apply an impulse or a short pulse. Then we want to find Kp such that the output over time has this form. So how to do that? We start from 0 and we keep on increasing Kp until stable oscillation is observed. Then we read the period of such a stable oscillation. Graphically, we have the following scenario. We keep on increasing Kp until we observe a stable oscillation. Then we observe the period of this stable oscillation, and this period is denoted by L. This period is also called the critical period or the ultimate period. And this period L is an input parameter for the design of the PID controller. Another input parameter is the critical value of the proportional gain that produces the stable oscillations. And this gain is called the critical gain or the ultimate gain. Once we determine the critical gain and the critical period, the Ziegler Nichols method determines the parameters of the PID controller by using this equation. Kp is simply 0.6 multiplying the critical gain, Ti coefficients that affects the integral gain is 0.5 times L, and remember L is the critical period, and the derivative coefficients is 0.125 multiplying the ultimate period or the critical period. On the other hand, if the controller is the PI controller, then the parameters are given by this equation. And that's it. That's the whole idea of the Ziegler Nichols tuning method. Let us now explain how to use this method by using the following example. Here is our plant. It's a third order system. It has poles at 0, -2, and -3. This model is used to simulate the response, that is, to generate the output. However, during the tuning process, we assume that we don't know this planned model. We only use the measured output of this model to obtain the response data, since I don't have here an experimental setup that I can use in order to illustrate the Ziegler Nichols method. So only on the basis of the observed response data, we perform the PID control tuning. And I will use MATLAB to generate the outputs. I will present the MATLAB codes at the end of this video. The first step in applying the Ziegler Nichols method is to find the value of the gain that produces stable oscillations of the output. So what do? I start with a small value of Kp. For example, Kp is equal to 5. Then over here, to my reference signal, I either apply a short pulse or an impulse. Then I observe my response. And here's the observed response. So for Kp is equal to 5, you will see that the output goes up, and after some time, the output goes down and it goes to 0. This means that this value of Kp is not producing stable oscillations. That is, for this value of Kp, the system is asymptotically stable. So we need to increase the value of Kp. Next, we increase Kp to 25. And here's the observed output. Wow, we can see that the observed output looks a little bit better. The oscillations are starting to happen, however, they die out after 40 seconds. This means that we need to increase Kp even further. That is, we need a larger number for Kp. Now you can start playing with the values of Kp. However, in order to make this video as short as possible, I will present the value that produces the stable response, and this value is Kp is equal to 30. And for Kp is equal to 30, we see a pretty much stable response. Now, if you would increase Kp, for example, to 31, you will see that over time, this response will explode. That is, this Kp is some kind of a limit of stability of the system. And this is our critical gain. The next step is to measure the period of the stable oscillation. Here's my period, and by reading this graph, I figured out that L is approximately equal to 2.75. So this is my ultimate period, or the critical period. So Kp is equal to 30, and this is the critical value, so that's why I have a star over here. And my period is equal to 2.75. Now, by using these two parameters, that is, these two values, I will design my PID controller. And as you can see, you don't need the model of the plant in order to design the PID control parameters. So how to design the parameters of the PID controller? Well, we'll simply go back to our original equations, that is to the equation number 3, and we substitute the value for Kp star and for L. And the substituted values are given over here. As the result, we obtain Kp of 18, Ti of 1.375, and Td of 0.3438. Now, our PID controller looks like this. We obtain this form by simply multiplying the terms in the PID controller. And by substituting the values, we obtain our final PID controller. So let us simulate this PID controller and let us see its closed loop response. So here is the step response once I simulate the PID controller in the closed loop. So I have my PID controller, I have my plant, I have an output, and over here I have a feedback signal, and I have my reference signal. And as the result, your output will behave like this. And we can immediately see a problem over here. Look at this overshoot. This is a very, very bad overshoot, and we want to decrease this. So how to decrease this overshoot? Well, we obviously need to increase the damping of the closed loop system. And how to increase the damping? Well, you can increase the dampings in many ways. For example, in this video, I will increase the damping of the system. That is, I will reduce the overshoot by increasing one form of action of the PID controller. That is, I will increase the derivative action. So after increasing the derivative action, for example, I can take the original derivative of action computed by using the Ziegler Nichols method, and I can increase it for 2.5 times. Then This will actually have the following effect on the closed loop response. By increasing the damping, yes, we are going to dampen the output. However, we will see that our response is slower. So, to improve the response, that is to improve the rise time of my system, I will increase the integral action. We can increase the integral action by decreasing the parameter Ti, this parameter over here. This is because the integral action is inversely proportional to Ti, as you can see over here. So by using this formula over here, we can compute the second controller or the new PID controller, and let's simulate this PID controller. And here is the simulated PID controller. This line over here represents the response of our initial controller, whose parameters are computed by using the Ziegler Nichols method. And the second line, that is the line over here, represents the response computed by increasing the derivative action and by increasing the integral action. And we can see that we have significantly reduced the overshoot, and we have even improved the rise time of the system. Okay, next, we explain the MATLAB code we use to generate these nice graphs. So here's the MATLAB code. First, we close all the windows, we clear our memory space, and we clear the workspace. And the first step is to define our open loop function, that is to define our plant. Here's our plant. It's given by the equation number 5. We use the MATLAB function ZPK, that is zero pole gains, in order to specify the plant. We don't have zeros. You can see that since you don't have any polynomial non-zero value over here, right? And we have 3 poles. The poles are at 0, -2, and -3. So going back to our function, we simply say ZPK, we specify the zeros, poles, and gains, and here's our open loop function. Obviously, it's correct. Then, let's design a proportional controller. Here, I specify the proportional controller, and I will specify its gain. For example, the gain should be equal to 16. Here, I create a closed loop system. I simply use the MATLAB function feedback. I specify proportional controller times P, and I have as a feedback 1. This function automatically assumes that you have a negative feedback, so consequently this is basically -1 in interpretation inside of the MATLAB code. So if you want to have a positive feedback, you will put here -1. However, we want to have a negative feedback, and this is our open loop controller times P, and let us compute an impulse response. So let's see what happens. Okay, so here's the impulse response for Kp is equal to 16. So let us increase Kp, for example, to 30, and let us see the response. Let's see what happens. Okay, so here's the response, and this is the graph I explained previously, and from this graph we can obviously read the critical period. Okay, now we can compute the parameters by using the Ziegler Nichols method. Here's the implementation. I take my Kp that's equal to 30, I take my critical period, and I compute my Kp, Ti, and Td. The next step is to define the PID controller. We simply apply this formula, and the formula is basically given over here. So this is the initial formula for the PID controller. However, once we multiply these terms in the numerator and the denominator, we obtain the final form of the PID controller given by the equation 7, and this equation 7 is given over here. Then we can simply verify this PID controller by computing ZPK model, and here is the ZPK model. Now, very important thing to observe is that this PID controller has a double zero. It has a double zero at minus 1.455. We can also compute the Bode plot of a PID controller. You can see this is a typical Bode plot of the PID controller. We have a phase lead at higher frequencies, and this can be used to improve the basically PM, that is basically the phase at high frequencies, in order to have a better response. Next, we create a closed loop system by using a newly defined PID controller. So let's see what happens. Here's the new closed loop system, and we simply simulate in the second graph our controller. Here I will close this window and let us simulate the new controller, and let's see what happens. Okay, so this is the basically PID controller, and its effect on the closed loop system, and we can obviously observe a very high overshoot. So let us reduce this overshoot. We can reduce this overshoot by increasing the integral gain and by increasing the derivative gain. So I simply increase the integral gain by decreasing the TI parameter, and I improve or increase the derivative gain by increasing the TD parameter. So let us simulate this controller, and let's plot all the results on the same graph. And let's see the results. Again, I will close these two windows, then I will run the code from the beginning, and let us see the responses. Okay, so here's our response. This is the initial controller, its closed loop response, and the second graph is improved step response from the beginning of this video. Okay, so to summarize, I explained you how to apply the Ziegler Nichols method. To apply this method, you don't need to have a model of the plant. Now, how can we improve this design procedure by including the model of the plant? Well, the idea is to find the gain, Kp, that will produce stable oscillations on the basis of the model of the system. Now, let's see how to do that. The first step, of course, is to set derivative and integral actions to 0. And this is our proportional controller. It's given by the equation 12. Next, the closed loop characteristic polynomial is given by this equation. Basically, the transfer function of the system that looks like this is output is equal to Cp over 1 plus Cp multiplying the reference signal. The characteristic polynomial determines the poles of the system, and the characteristic polynomial is equal to this equation. So from this equation, we can obtain the characteristic polynomial, and here is the characteristic polynomial of the system. This polynomial can be written in this form by simply multiplying these terms. Self-sustained oscillations occur when the zeros of the characteristic polynomial are purely imaginary. That is, the zeros should have this form: S is equal to J omega. By substituting S for S is equal to J omega in the equation number 15, we obtain the equation number 16. Now, the complex polynomial is equal to 0 when both its real and imaginary parts are 0. So what is the real part over here? The real part is Kp minus 5 omega squared, and the imaginary part is minus omega to the power 3 plus 6 omega. and both the real and imaginary parts should be equal to 0. And this is exactly the equation number 17. Let's solve the equation number 17. Omega cannot be equal to 0, so omega 0 is not the solution. From the second equation, we obtain this equation. That is, we can solve the second equation for omega equals to square root of 6. Now, we know that omega is equal to 2 pi over L, where L is our critical period. So, by using these two equations, we obtain the equation number 20, and we can solve for L. And the critical value of L is equal to 2.5651. Now, stop here for a second and remember the value of L that I read from the graph. The value of L was 2.75. So, our heuristic or experimental method gave us a relatively good estimate of the true value of L. Now, by using this equation, omega is equal to 6, we can substitute omega in the equation number 17, and we can obtain this equation over here. We can obtain the equation number 21. And from the equation number 21, we can see that the critical gain is equal to 30. And this is precisely the value that we found experimentally. To summarize, we learn how to use the model of the plant to quickly determine the critical period and the critical gain that can be used to design the Ziegler Nichols PID controller. And this approach is possible because we know the model of the system. Now, in practice, you will never know accurately the model of the system. You will know some nominal model that's not exactly equal to P of S, however, it can approximate relatively well P of S. Then you will, instead of, let's say, 30 for the critical gain, obtain Kp is equal to 25. And once you simulate the system, or you basically not simulate, once you do experimental measurements on the system, you will see that this Kp does not produce stable oscillations. Does this mean that this method is useless? No, it's not useless. It's actually very useful, since this Kp can be a good starting point for increasing further the value of Kp in order to find the critical gain. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.